Next speaker, it's a pleasure to introduce Julian Kupka from Hertfordshire University, who will tell us about recent advances and twists of n equals 1, d equals 10 supergravity.
All right. Thank you for the nice introduction. Can you hear me well? Or okay. Yeah, first of all, thank you for the introduction and having me here at this conference. Wrocław is a really nice city and I quite enjoy being here. Also for the Polish people in the audience, have fun with my last name, or ask me later about it if you don't speak Polish. Yeah, I'm a PhD student at the University of Hertfordshire, and my talk today is based on joint work with Friedrich Wallach and Kayla Bionka, who are at Charles University in Prague, as well as my supervisor, Charles Strickland Constable, and Ingmar Seberi, who are at the University of Hertfordshire with me as well. And my talk is going to be a little bit of a change of pace, I suppose, because it's a lot about supergravity. And what I want to tell you about today, or my goal is to convince you of a framework called generalized geometry and its usefulness in describing supergravity and so-called twists of supergravity. And for that, I want to tell you what these twists are and telling you what the Costello-Lie twist conjecture is. Then I want to tell you what generalized geometry is and how we can use it in supergravity. And then how we leveraged it to formalize or formulate the BV formalism of supergravity. And then lastly, I want to introduce to you the current contact model, which is trying to tie together all of the things above. So let's start with the Costello-Lie twist conjecture. And the conjecture itself is relatively straightforward. The conjecture namely says that the twist of supergravity on a Calabi-Yau fivefold, so in 10 dimensions, is BCV theory. And I guess for most of you, and also for me, this is not very enlightening. This is more of a word salad. So let's break this down. This conjecture has two sides. Namely, it has the twists of supergravity. And the idea here is such a twist is given by, once you have the BV action of supergravity, you pick a so-called twisted background, which is a weird background where a ghost for supersymmetry, which is a bosonic field, gains some non-zero vacuum expectation value, and then you expand around that. And then on the other hand, on the other side, you have the so-called BCV theory or Kodaira-Spencer gravity, which basically is a holomorphic theory that describes the massless sector of twisted string field theory. And the important bit for us today is that it admits some kind of mathematically rigorous defined quantization. So the punchline of the conjecture or proving the conjecture is the following. It would give us some kind of rigorous definition or construction of at least a subsector of quantum gravity. Or at least that's what I would write in a grant application if I need to get money. So the conjecture is quite nice because it is very constructive. But it is quite difficult to actually prove the thing. Because first of all, for the longest time, the supergravity BV action for the n equals 1, d equals 10 theory was not known. And also the right-hand side is then quite complicated to align with what I've written on the left-hand side. And I want to explain to you how we use generalized geometry to make both sides of this conjecture more tractable. Does it work? Yes, cool. So let's talk about generalized geometry, the best thing ever, in my opinion. And it starts from the following idea. So if you start with the bosonic fields of n equals 1, d equals 10 supergravity, namely you have some kind of metric G, you have a two-form field B and the gauge connection A, as well as some kind of dilaton field, which is just a function. Then you can look at the bosonic infinitesimal or local symmetries of that thing. And they are given by diffeomorphisms, represented by vector fields, one-form symmetries, and gauge parameters, or gauge symmetries. And let's already collect them in a nice object that at least locally looks like the sum of the three things. And then the diffeomorphisms act via the Lie derivative. Your one-form symmetries act on the B field by the exterior derivative of this parameter. And then gauge transformations are gauge transformations. And if you look at this for a second and think about the bracket of, for example, a diffeomorphism and a one-form symmetry on your B field, you notice that you get some kind of non-trivial bracket on that. And if you take the structure very seriously, it lets you, like this bracket lets you define a very nice structure on this thing, the so-called generalized tangent bundle E. Namely, you can give it the structure of a so-called Courant algebroid. And what is a Courant algebroid? It's some kind of vector bundle E, which is some kind of anchor map to the tangent bundle. It has a nice bracket on it and some inner product plus some axioms. And for the purpose of this talk, it's not working very well, very good. The bracket takes this rather complicated looking form. And the exact thing here is not too important, but you can see there's some Lie derivatives appearing from the left-hand side on the right-hand side, but it's not quite antisymmetric. Like it doesn't go the other way around. And this is part of the axioms. So this bracket that we defined above defines satisfies the Jacobi identity, but it's not antisymmetric. But at least it's not antisymmetric in a very controlled way, where you have the exterior derivative of this inner product. And these capital letters here are generalized tangent vectors, so they are sections of this bundle here. Once we have the structure in this nice bracket, we can define the so-called generalized Lie derivative in the same way you would define the normal Lie derivative, where you just take a generalized vector and map it into the first slot of your bracket. Yes? No. So this is the standard bracket on the transitive case, where you have included here a gauge bundle, basically. It looks different from the type 2 case. That's a very good statement, which I sweep. So there's a lot of things I'm going to sweep under the rug today. And this is one of these things. Thank you for the great question. As a quick side remark, because it's going to appear later, this generalized Lie derivative has a non-trivial kernel, because these transformations have a redundancy if you put something exact here. Okay, so this is the background for generalized geometry, this generalized tangent bundle, and now let's do some geometry on this thing. And it turns out that there's a really nice thing you can do with most of your bosonic fields. You can take your metric, your two-form field, and your gauge connection, and you can map this into this curly G, the so-called generalized metric, which is now an endomorphism on your generalized tangent bundle that squares to the identity and is symmetric. And because I'm going to use this notation later on quite a bit, first of all, notice because this squares to the identity, it gives a positive and negative eigenspace in which you can split your generalized tangent bundle. And we have adapted frames. So if you have a Latin index somewhere, you see a Latin index, this corresponds to C+, and you should think of it as a tangent bundle index. And then you have your Greek indices, alpha here, for example. They correspond to C-, and they roughly correspond to a copy of the tangent bundle plus gauge indices. Then furthermore, you can also encode your dilaton nicely, your generalized dilaton, which is given by a Noah vanishing half density. So a thing you square and then can integrate over. And the idea here is that you define it in such a way where you square this half density, you recover the metric density times your old dilaton that you had before. And then it turns out that, so first of all, this is a really nice and efficient repackaging of all these bosonic fields into only two objects. And then the bosonic symmetries are simply realized by this generalized Lie derivative that I defined above. Cool. Yes, exactly. There's a different, exactly. This is slightly different from what people sometimes do is ODD times R geometry, where you have the dilaton is in some kind of other structure. We have basically two structures here. We have the generalized dilaton and the metric as two independent degrees of freedom. Cool. Okay, it's supergravity. So let's add the super part, which means we need to add fermionic fields. And one technical detail is we assume the existence of Mariana-Weyl spinors, but only over this bundle C+, and not over C-. This works for the n=1 theory, and it's quite a nice technical simplifications, because your Clifford algebra will only have Latin indices instead of Latin and Greek indices. Okay, then you take your ordinary fields of supergravity. First of all, you have a dilatino, corresponding to the dilaton, of course. And the generalized dilatino is not as interesting. One thing we do here is that with all spinors, we take to be spinor half densities. So we weight them by some half density factors, which makes the supersymmetry transformations much more simple. And then more important or more interesting is you can take the ordinary gravitino and the ordinary gaugino, and you can map them into a single object, the so-called generalized gravitino, which again is a spinor half density, and now it has a C- index attached to it as well. And by what I just told you about the Clifford algebra, and it seems like a small detail, but it led to like huge simplifications. The Clifford algebra has an index in C+, this in C-, and you cannot contract the two with each other. So there's much less spinor bilinears that you can actually write down. In addition to fermions, we also have generalized connections. And without going into too many details, I just want to make you aware that a generalized connection is really a different beast from a connection on a vector bundle, because it takes a section of your vector of your generalized tangent bundle, and then here instead of a vector that eats a vector, it eats again a generalized vector. So it's very different, in fact. We can then define something which is what meets Levi-Civita here, namely this generalized derivative, covariant derivative is compatible with the generalized metric, the generalized dilaton, and its torsion is equal to 0. And by a relatively straightforward counting argument, you can show that this actually does not uniquely determine your connection. which seems bad at first, right? Because if you don't have a unique way of writing down your connection, you're kind of screwed. But it turns out that you can define some unique operators. And among these operators is, first of all, the generalized Ricci scalar, the Dirac operator, and then the derivative along these minus directions. And funnily enough, it turns out that these unique operators are exactly the operators you need to write down supergravity. So again, if you break down this generalized metric into its component fields, then you can roughly break down this generalized connection into a normal Levi-Civita connection, some H flux, and some the field strength of the gauge bundle, plus some derivatives of the dilaton, which I forgot to write down here. And then the single term, the single generalized Ricci scalar, is equal to the thing you need to, like the whole bosonic action of n equals 1, d equals 10 supergravity in one object, which is quite neat. Furthermore, the spinor operators above are exactly what you need to write down the supersymmetry transformations and the fermionic kinetic terms. So in this sense, you can see generalized geometry gives a huge simplification of n equals 1, d equals 10 supergravity. And I'm going to show you the full action in a bit, and you can see that it's much simpler. Exactly. Yes, this is you. Well, no, this is not. This is a unique operator, so it doesn't depend on the choice. Yes, this does not depend on the choice. If you just look at the contractions you have to do, all the undetermined components drop out. Yes. Cool. As a quick aside, in my formalism or in our formalism, we do not have any gauge Lorentz transformations. We only have generalized Lie derivatives and supersymmetry. And this leads to a very, very interesting structure that unfortunately I don't have time to talk about, but please feel free to ask me later about it. Cool. So now we know what supergravity is and how we use generalized geometry to formalize it. Let's talk about the BV formalism. And I assume that most of you haven't encountered it much, but think of the BV formalism as BRST on steroids, because that's really all that is. And we have the following setup. We have some kind of physical fields. We have some kind of action governing the dynamics. And then we have some gauge symmetries given by these delta operators. And then we assume that these symmetries form a very, very generic algebra. Namely, you have some kind of commutator on the left-hand side. You want that the commutator, again, gives some kind of gauge transformation with some kind of bracket of the parameters. And then you have stuff that only vanishes on shell. And these golden terms, M here, govern how this algebra only closes on shell. For this bracket of this parameter, we make also a very generic ansatz. Namely, this bracket does not need to be, or it can be field dependent, it can be not Jacobi, and it doesn't need to be antisymmetric or anything. And this is roughly exactly the statement or like the case we have for supergravity. Okay, and from this data, we want to construct some kind of operator, some cohomological operator, such that at least the zero cohomology is gauge invariant stuff up to stuff that vanishes on shell. How do we do that? We basically follow the ansatz of BRST. So we introduce ghosts for each symmetry, which are parity shifted. If you have gauge redundancies, you need to introduce a ghost for ghost. And then if you want to look at least at the linear part of this operator, it should more or less generate these variations for your physical fields. And then for your ghosts, they should transform under the bracket plus their gauge redundancies. Furthermore, you need to introduce conjugate antifields, roughly speaking, just to have some way of deal with these equation of motion terms. And because these are like conjugate fields to your normal fields, you can define a degree 1 shifted Poisson bracket. So you're in the setting of graded Poisson geometry. And then you make the following ansatz, or have the following idea. Instead of talking about this BV operator, you can assume that it is generated by some kind of Hamiltonian flow. And you have a degree 0 BV action. And then the fact that this operator squares to 0 is equivalent to the so-called classical mass equation, where this BV action Poisson commutes with itself. And then the meat of the formalism is taking this input data and somehow writing down, finding a way to write down this BV action such that it encodes all of this information and satisfies this classical mass equation. Very good. Okay, so now let's do that for supergravity. As I said, in our formalism, we only have generalized diffeomorphisms. They are less interesting here. And then we have the supersymmetry ghost, which again, because of the shift here, is now a bosonic field. In addition, we have a ghost for ghost term because of this gauge redundancy. And then we were actually able to show that the BV action of n equals 1 equals 10 supergravity takes a relatively straightforward form. in the sense that it only has 3 terms. The linear term in the antifields is completely determined by this variation, and the quadratic bit is completely determined by how this thing vanishes on shell, this algebra. And then we were also able to show that the whole thing actually satisfies the classical master equations, and we think we're probably among the first people who have actually shown the full calculation, and it's in the full paper. And like the result takes this relatively straightforward, simple form. At least it fits on one slide, so it's not super simple, as you can tell. But if you now just look at the first line, which is made up of 6 terms, compare this now how this would look in ordinary geometry, because just the first line is equivalent to all this junk here. Sorry, not junk, all these terms here. And here I've written down the supersymmetry transformations, and this is just one of the symmetries we have in the other action. So it would be much, much more complicated to write it in ordinary geometry. Cool. So we now have the left-hand side of this twist conjecture. We have BV supergravity. So now we should be able to compute the twist. And it turns out we don't know how to. It's still a very, very hard problem, as you can tell by the many terms. And at least the hope is that we can make the problem a little bit more tractable by using more generalized geometry. Because, yeah, if you have a hammer, something about the whole world looks like a nail. And one thing we came up with is the so-called Courant contact model, as kind of like conjecturing what the right-hand side of the conjecture should be in the end. So let me briefly introduce that. If this works, very good. I'm going to now use some scary words that I only understand very, very superficially. So for this Courant contact model, which I will call CCM from now on, we have the following input data. We have some parameter f, which lives in a sheaf of DGLAs, which, again, scary word, but it just roughly means you either have smooth functions, holomorphic functions, or some Dober resolution of holomorphic functions. Then you have this parameter psi that lives in sections of an O-Courant algebroid. O-Courant algebroid is just a generalization of what I told you before to the setting of either the holomorphic case or some kind of Dober resolution of a holomorphic case. And then lambda, you can think of as deformations of 5 orientations. And the 5 orientation, which lives in this O-Schwieg dual, again, scary object, I don't really know what it is, but you can think of it in terms of it's either density, an orientation, or holomorphic volume form. And then once you have this data, these parameters, you can write down some kind of non-Darboux -3 shifted symplectic form that comes from some kind of potential. And it turns out this potential comes from a symplectification of a contract structure on field space. And this is where the name Courant contact model comes from. Then furthermore, in these parameters, you can write down some kind of action that takes a relatively simple form. And we were able to show that this satisfies the classical master equation. So the whole thing describes some kind of BV theory. And if you look what this BV theory describes, it describes the moduli of 5 orientations up to generalized diffeomorphisms. So it's a very cool deformation problem. The punchline here, though, is the Courant contact model gives us a handle to crank. You take as input data an O-Courant algebroid and an orientation, and then the CCM theory gives you a BV theory in the end. And this is just mathematical nonsense, so let's connect it to something physical, namely twisted supergravity. So it turns out one of these twisted critical points of this BV action gives you a pure covariantly constant bosonic spinor, meaning that it lives in the kernel of the Dirac operator. It is covariantly constant along the C- directions, and it doesn't generate any vector part. And you can use this to define an interesting subbundle, basically by the annihilators of this bosonic spinor, which already gives you a complex structure on your base, just from this data. And then, sparing you a lot of details, you can use this bundle L to write down some holomorphic Courant algebroid, which roughly looks as the sum of the holomorphic tangent bundle, holomorphic cotangent bundle, and here's some adjoint holomorphic bundle. And then you can Dober resolve the whole thing, and the whole thing gives you some Dober Courant algebroid. In addition, from this E, you can square it and extract the 5 form part of it. This turns out to be a 5 orientation. So in total, the punchline of the construction is the twisted background gives rise to some kind of input data for the CCM. So we can take the twisted background and output some kind of holomorphic BV theory. I'm going to quickly come to the end here, which now leads us to 2 questions. What does this Courant contact model for this twisted background describe, and how does it relate to BCOB? So the first question is answered by the CCM gives rise to some kind of theory that my supervisor wrote down that computes the moduli of D equals 10 heterotic supersymmetric backgrounds, which means the CCM computes something interesting in physics. And then we have a theorem where if you place this current contact model, you take this data and put it back on a Calabi-Yau fivefold. This is equivalent as a BV theory to BCUV theory. So the CCM contains BCUV theory. And instead of us solving the conjecture, this gave us the opportunity to shift the goalpost a little bit and to write down the extended Costello-Lee conjecture, which simply states the twist of n equals 1 supergravity in 10 dimensions is the current contact model for the twisted background. And this is now a setup where you have arbitrary gauge fluxes and everything turned on. So it's like a very, very generic statement. We're still not able to prove this, but at least we found a generalization and a nicer reformulation of this conjecture. And yeah, with that, thank you for your attention, and I hope you enjoyed the talk.
Other questions?
Hi, thanks for the talk. I can't see how this generalized geometry language helps in any way to getting closer to proving the conjecture. What's the intuition? It feels like a very nice repackaging where you can rewrite your action very nicely, but the strength of the conjecture has like a lot of implications.
Mm-hmm.
And yeah, perhaps some intuition on how this could get us closer.
I guess it is really just about the repackaging at the end. Or like, it has multiple things at once. So first of all, it's a very efficient repackaging. And I always like to compare it on solving Maxwell's equation in the formalism he wrote it down, where he had like, I think, 21 coupled PDEs. Compare that to the modern formulation in tensor calculus, where you have 2 equations that you need to solve. So it becomes much easier to reason about in generalized geometry. But then on the other hand, generalized geometry is really cool because the objects you define, you can define them for arbitrary flux backgrounds and gauge bundles turned on. So it's and it hides all of this data in this generalized metric, for example, this generalized Levi-Twitter connection. So it's a nice repackaging. That's one of the upshots. Another upshot of this formalism is that you can start thinking about models that are non-physical and which can give rise to really nice toy models. For example, we've written a paper called Supergravity without gravity, and it's BV formalism, where we write down some kind of very small model, which actually had all the features of the BV supergravity that we needed to solve the full case. And it turned out that this very small model gave us almost all the insights we needed for the full calculation. I don't think I fully answered your question. And as I said, like what we really do here is we shift the goalpost. We are not much closer to solving the conjecture, as far as we know. We just think we have a better formalism and a better handle on it for future work. Thank you.
Thanks for the really nice talk. So a quick question about, so is the BCOV theory you're deriving the one that, like from the 95 paper? Because obviously in that they take like the 2-2 sig model and they do a twisting and they write down the field theory for this.
Mm-hmm.
And the action for that is very weird and obviously motivated from diamond diagrammatics and quite unsatisfying. So you're saying you can take your supergravity background, do this twist, and you can maybe, is there a mechanism to get to that action from a more natural perspective?
Well, again, like in gray, as I said, there's a lot of things I sweep under the rug. And one important thing, the BCUV you're referring to is probably the type 2 thing.
Yeah, exactly.
Type 2 theory, which is not because we look at the minimal type 1 BCUV theory. There's like a lot of different BCUV theories.
So this is going to lead to my next question. So like, where does the data of like the Beltrami differential and complex structure deformations come in? That's what like BCOV's dynamical field is, right?
Yes. So if you look at the action. So I don't remember the full details, but luckily we break it down how it. So in our my second to last paper, we've shown this isomorphism because it's a change of variables from this theory to BCUV on the Calabi-Yau fivefold. And if I remember correctly, the Beltrami differential is somehow encoded in this term. But it's kind of muddled up with all the other deformations as well. Because in generalized geometry, you don't really distinguish between between vectors and covectors. So, and the Beltrami differential is kind of like the vector part of that, like the Doppler resolution of that. So it's not immediately clear, but the change of coordinates is rather straightforward. And yeah, look into the paper there, like all the details are there.
Okay, then in view of time, thank Julian again.
Thanks so much.
So now we have a lunch break.